So we're going to talk about nuclear energy. So in general, when we talk about this, it says that this unit's nuclear physics, and we call that mostly so that people remember it. But really, this is about modern physics. And the trend of modern physics really started with the study of the atom and the atomic bomb. So back in the late 1930s, early 1940s, when they were doing this thing that most people know as the Manhattan Project, that really is what kick-started modern physics. And when I say kick-started it, one of the things, and we'll talk more in detail about the Uranium Committee and the Manhattan Project, but what I want you guys to know right off the bat is that they put a bunch of people, a bunch of scientists and engineers together, and they gave them a bunch of money, and they did a bunch of research. And essentially in like 2 to 4 years, they did the equivalent amount of research that usually would take like 100 years. And because we did that, we advanced our knowledge in many different areas very quickly. And so that's, when I say kind of kicked off all of modern physics, this is what I'm talking about. So let's talk about this. So in order to understand things like atomic bombs and all of this, we got to start simple. So a lot of these things that we're going to start with, you should know from your chemistry class. And if you know them, great. If not, well, then you should write this stuff down because it's critical knowledge that you need going forward. So, to start off with, we have a review of the periodic table. So it says elements in the periodic table represent the most commonly found elements in nature. Okay? And so when you see an element in the periodic table, it'll have different numbers with it. For instance, I have a periodic table there on the wall. Do y'all see the little blue numbers up on the wall? What do those little blue numbers represent? Yeah. Well, yeah, it's the atomic number. It's the number of protons in the nucleus. And so it says that right here, the number of protons in the nucleus. And so the way you see it written on a piece of paper is usually one little number over another number. So the atomic number will be the bottom number. And then what is the number that's written in red up there represent? Yeah, it's the atomic mass number, or the mass number as written on the top here on the slides. So these are two numbers that give you information about the element. So the atomic number is the number of protons. The mass number is like the total number of nucleons in the nucleus, or what we say, the number of protons plus the number of neutrons. So when you see this stuff, what's interesting is if you look at the periodic table, or most periodic tables, that red number, or the number on the bottom on the periodic table, is generally not a whole number. Which is interesting because these are the mass number. It's just simply the number of protons plus the number of neutrons. They should be a whole number. But as that first statement says, that the elements in the periodic table represent the most commonly found elements in nature. Which means that they have a thing called isotopes. So let's talk about that. So an isotope is a form of the same element. It just happens to have a different number of neutrons. So again, when we're talking about chemistry here, the thing you have to realize is that what we call an element is based on the number of protons only. Everything else can vary. So if an element has, let's say, 6 protons, we call that thing carbon. If it has 8 protons, we call that oxygen. Now, the most common form of oxygen has 8 protons and 8 neutrons. And so it would have an atomic mass, or the mass number, of about 16. But if you look on most periodic tables, oxygen doesn't have 16 written for its mass number. It has 15.9994. What is that? Well, the thing is if we take all of the different oxygen that we can find and we test it, we find that most of them have, say, 8 protons, but, sorry, all of them have 8 protons, but most of them have 8 neutrons as well. neutrons in the common form, we call that an isotope. So for example, right here on the slide, you can see that this is talking about carbon. So carbon-12 is the most common form of carbon. And it says right here, carbon-12, carbon-13, carbon-14, they all have 6 protons, okay? But carbon-12 has just 6 neutrons. And that is the most common form. As it says right here, down at the bottom, it says abundance. Abundance is 98.89%. So that means if you just grab a random carbon atom, chances are it's going to be carbon-12. It has a 98.89% chance of being carbon-12. It is the most common form of carbon. There are other forms though. So for instance, it talks about carbon-13, which happens to have 1 extra neutron. But there's also carbon-14, which has 2 extra neutrons. And as it says right here, carbon-13 it's basically 1.1% of the carbon you find. So occasionally you will find a carbon-13. But carbon-14 is extremely rare. Carbon-14 you almost never see. It says carbon-14, the abundance is 1 part per trillion. That means if you have a trillion atoms, chances are 1 of those trillion atoms is carbon-14. Now what's interesting here is that's the definition of an isotope. So is everybody clear on that? An isotope simply has a different number of neutrons. It could have more, as in these examples, but it could also have less. Everybody okay with that? Now if you look down here at the bottom of carbon-14, it says that carbon-14 has a half-life. What that means is that carbon-14 is radioactive. The main reason why you have a common form of an element and then all of the other isotopes is because the isotopes are unstable, which means given enough time, they will decay or change into something else. And that's what we're going to talk about over the next couple of classes, is that these elements, these isotopes, the reason why they're not terribly common is because they tend to be radioactive. So here, this slide talks about fundamental forces. So it says atoms are held together with forces, otherwise they would quickly fall apart. What I think is interesting is you guys learned a long time ago about the electromagnetic force, right? We talked about 2 electrons, you bring 2 electrons together, they repel. 2 protons together would also repel, but an electron and a proton should attract. Everybody goes, okay, that's cool. I just told you, if you didn't know this already, that inside the carbon nucleus there are 6 protons. What's the charge on a proton? Positive. So should those protons attract or repel each other? They should repel. And they do. But they're still stuck together in that nucleus. Well, it turns out there's more than just one force. As far as we can tell right now, there are 4 fundamental forces. Those forces, 2 of them you guys know pretty well. The weakest one is gravity. The second weakest is what we call the weak nuclear force. The third weakest, or second strongest if you will, is the electromagnetic force. And then the strongest force that we can tell is what we call the strong nuclear force. And it turns out that if you get just 2 protons and you try to smoosh them together, that electromagnetic force does not want them to get together. It's going to repel. But if you keep mushing them closer and closer, closer and closer, eventually, if you apply enough energy, enough force to get them together, they will stick. Because of the strong nuclear force. The strong nuclear force, as indicated by the name, is stronger than even the electromagnetic force, which would want to push them apart. Now the thing is, they still want to repel because of the electromagnetic force, but the strong nuclear force, as indicated, is stronger, and it will hold them together. But the problem with the strong nuclear force is it's incredibly strong, but it has a very short range. So you have to get these things really, like, absurdly close together. And in most cases, they never come anywhere close enough for the strong nuclear force to hold them together. Sometimes they do. And as we go through these notes, this class and next, neutrons. And so that's one of the reasons why you tend to find very quickly neutrons in the nucleus, because yes, two protons can stay together just by themselves with just the strong nuclear force, but again, that electromagnetic force does want to push them apart. And so they don't tend to stay that long. And so typically what happens is that you get a proton and a neutron stuck together, because the neutron is not going to have that repelling force. It will still have the strong nuclear force. But then you can add in another proton, and between the two protons and the neutron, there's enough strong nuclear force to overcome the electric force. So again, typically as you get more protons in the nucleus, you need more neutrons. And at first, it's kind of a one-to-one ratio. You add a proton, add a neutron, add a proton, add a neutron. But at some point, simply adding more neutrons isn't enough to make the nucleus stable anymore. And you're going to have to add more than one neutron. Which is why very quickly, like carbon has 6 protons and typically 6 neutrons. For instance, uranium, number 92 there on the periodic table, has 92 protons, but it has 146 neutrons, because it needs more just to hold it together. This video here is by Michio Kaku, and he talks about the 4 fundamental forces. So you can watch that on your own. He essentially talks about the standard model of physics, which we're not beyond the scope of this class, but the standard model is, well, the model we use today. So, if you're looking at a periodic table, you'll notice the element uranium, number 92 on the periodic table. Everything past that has a label called transuranic element, means past uranium. So uranium is number 92 on the periodic table. So, like, for instance, number 93 on the periodic table is Neptunium, and number 4 is plutonium. Anything past number 92 is considered a transuranic element. And that doesn't just mean, oh, it's past uranium. If you're looking at this periodic table here on the wall, you'll notice that those elements have different colors. You'll see that? What do you think it means if an element is written in black? And not just a metal. It's a good guess. What form of matter is the metal? Solid. If it's black, it's a solid at standard pressure and temperature. You'll notice most of them are black. Some of them are red, though. What do you think red is? It's a gas under standard pressure and temperature. Notice that all your known gases are, well, gases. Right? There's a couple others in there. What do you think the blue ones? Yeah, but what is number 8? What is number 8? What does HG stand for? Mercury. So if it's written in blue, it should be a liquid at standard pressure and temperature. But there's one more color up there. So solid, liquid, gas, I think that makes sense. Chromium. Why is it white? Why is it white? So that's the other color, white. Y'all see the white color? It just looks like it has an outline. When it's white, that's interesting because the reason why it's white is because we haven't seen enough of it to actually know if it's a solid, liquid, or gas at room temperature. White elements are what we call inherently unstable. That we can make them in a lab, they are literally artificially made in a laboratory. Like we've made everything up there that's in white. Plus, that's an old periodic table. It's got, we got more elements than that now. But the whole point is if it's written in white, we don't have enough of it to know how it should act under standard pressure and temperature. So for instance, yes, number 43 is white. Because it's just not stable enough for us to have seen any of it. Now we can make it, it just doesn't hang around very long. And when I say we make it, I'm talking about some of these things only hang around for fractions of a second. Some of them can hang around a couple of days or weeks. But what I want you guys to understand here is that there's a couple of white elements before uranium, but notice that after uranium, they're all white. Okay? They're all white because they're all artificially made in the lab. We can make these elements, we just don't know what they would look like in nature because we can't find them in nature. And the reason why we can't find them in nature is the same reason why those isotopes aren't really found in nature anymore. It's because they're all radioactive, which means given enough time, they will just fall apart. Okay? So here it talks about exactly what makes a transuranic element. Sometimes the decay happens over seconds, sometimes the decay happens over thousands of years, okay, or millions, or more. This video we'll probably watch here a little bit after we finish the notes. This is a very interesting video about the most radioactive places on Earth. There are three basic types of radioactivity. And I say basic types because these are the ones that were found by Marie Curie. So let me talk for a second about Marie Curie. Most of you guys have heard about her, but I don't think most people understand. Marie Curie, once upon a time, she was a student, okay? And when she was working on her doctorate, she went to her professor and she was like, hey, I'm kind of looking for something to study my doctorate on. And he was like, I'm looking at this rock called uranium, trying to figure out what's going on there. Maybe you can look into that a little bit more. And she did. So what she did is she took this rock, and it's interesting because this rock, this uranium, actually comes from a mine, a silver mine, that is now part of, I think it's in the Ukraine, or the other country over there. I think it's in the Ukraine or maybe in Slovakia now. I can't remember exactly where. But it's over there, kind of in the, if you think about where Europe is and where Russia is, it's kind of in between them. So this stuff came out of this silver mine. Now what's the point of a silver mine? To get silver. And sometimes they would run into this other rock, which we call uranium. They literally, the word they use for it is translated as hard luck rock. Like if you hit this rock, it was just like, it's a really tough rock, it was hard to mine, and it was like, well, tough luck you hit that because there could be some like silver behind it, but you're gonna have a hard time getting through it, and this uranium stuff is completely worthless. Like, they would dig it out of the mine and they would just leave huge piles of it out in front of the mine. And some of them are still there. So what's interesting is that essentially when she started doing her research, this uranium, these rocks, were available to her for free. It was just like, yeah, you want to carry that big heavy rock out of here? Sure, take it. Then she could basically have as much material as she wanted, but her, leaning toward chemistry, she did something different. What's interesting is her mentor started studying uranium because of its weird properties that people were noticing. Like people used to make like uranium glass. And glass made with uranium is slightly tinted green, which is a little weird, but if you want green glass, sure, go for it. But what's really weird is that if you, say, have a ultraviolet light, the glass will fluoresce, which means it will give off a different color, like purple. So he was studying uranium to try to figure out what was going on with that, but she approached it from a much more chemical standpoint. So she took this rock and she started separating out the different elements in the rock. Because it's just a rock from the ground. It has no reason to be, pure silver or gold, whatever. Then she had to, refine it. And so she went through this process, and it turns out there was a lot of things in this rock. And as she started refining this uranium into its base elements that were in the rock with the uranium, she ended up finding one that is known as radium, number 88, on the periodic table. It turns out that when she separated radium into its pure form, just putting radium over there by itself, it turns out it was glowed green all of the time. And I don't mean like the uranium glass was tinted green, like if you looked at it, it was green, but when you went to bed, it was dark like everything else. But the radium glowed green all the time, 24 hours a day. And I think it makes a lot more sense when you realize that she was studying uranium, but then she finds this thing, this rock, that is just glowing all the time. Can't turn it off. That's a very strange thing. And there's a reason why, well, she started studying that. And when she started studying uranium and found this radium in it, people started using it for all sorts of things. They used it in cosmetic products, they used it in paint. Heck, there's still a, what do you call it, a hot spa in that town that they will put radium into the water. And you can take a nice radioactive spa bath. What's interesting about this is when she was refining this uranium into this, then uranium became worth something because you could get this radium out of it. At the time, 1 ounce of gold was worth 88 cents. No, 1 ounce of gold was worth 15 cents. 1 ounce of radium at this time was worth $88,000. Because you can't just get it, you have to do all these chemical processes to refine it. And so when she was studying stuff, particularly radium, she found that stuff would come out of it. This green stuff that's just glowing, those are visible light photons, but there's other things coming out of it, other things that we can't see but she could detect. You know, did she know what they were? No. So she didn't know what they were at first, so she just called them alpha, beta, and gamma. These are the three that she found. So an alpha decay, or alpha particle, she found that one first, and then she found a beta, then she found a gamma. She literally just called them alpha, beta, gamma because those are the first 3 letters of the Greek alphabet. So alpha decay is a nucleus that will emit an alpha particle. So we know, we can call it an alpha particle, or as it's more commonly known, it's a helium nucleus. That means it's a nuclei that has 2 protons and 2 neutrons, no electrons. Okay? It's just 2 protons and 2 neutrons. Because literally these nuclei are falling apart. And if you realize that, like, you take a nucleus and you rip a piece of it off, well, it's going to look like a smaller nucleus. And so one of the most common nuclei to come out is the helium nucleus. So again, 2 protons, 2 neutrons. And then later on, we figured out what the beta particles were. It turns out that they were from an electron. But that's weird, because it's not just like an electron that was orbiting the nucleus. No, these electrons come out of the nucleus, which is weird because do electrons belong in the nucleus? Do electrons hang out in the nucleus? No, and it says right there, beta decay is when a neutron decays into a proton. When that happens, charge is still conserved, so a neutron has no charge. So if a neutron becomes a proton, well then an electron will go shooting out of the nucleus, which should make a lot of people uncomfortable. And it did, even at the time. Fun fact, we're only going to study one type of beta decay, that type. This is technically called beta minus decay. There's another type of beta decay called beta plus decay, where a proton decays into a neutron. And in that case, an electron doesn't come out. Another thing called a positron comes out. The positron is an element, or a particle that is the same mass as an electron, but it has a positive charge. It is what is known as a piece of antimatter. And we'll talk more about that down the road. But I want you guys to realize that, first of all, there's a lot more going on here than we're really going to get into in this class. That's number one. And number two, if you're interested in that stuff, I can help explain it. But for instance, we're going to study beta decay, but we're not going to study beta plus decay. And I want you guys to realize that there's a bit more going on here. And the sad thing is we just don't have enough time to really explore it, but it's not required. But if you did, these things would make a lot more sense, and it would make you a lot less uncomfortable than just saying, oh, well, a neutron becomes a proton, and an electron, which you've never heard of before. And it's important to note that this is not chemistry we're talking about here. This is nuclear physics, okay? Or nuclear chemistry, if you want. So this is not your common things, but what's interesting is those rules and stuff that we learned in physics and the rules and stuff that you learned in chemistry still apply. Like conservation of charge still applies. Conservation of mass still applies. Conservation of energy, conservation of momentum still applies to even these concepts. The last one that she named was called gamma decay, or gamma radiation. She didn't know what it was. It turns out those were just gamma ray photons, which we kind of talked about in our last section on light. And usually gamma decay comes out after one of these other ones have already occurred. So then it defines a word up there. It defines transmutation. The definition of transmutation is when one element transforms into another, which you guys were probably told in chemistry does not happen and cannot work. That is called alchemy. Well, alchemy, we don't use that term in science because it has these negative connotations of like magic. Because essentially, if you say you're doing alchemy, like the common thing about alchemy was, oh, you're going to change, lead into gold, which you can technically do, but it is really not cost effective to do that. And so instead of using that, when people discovered this was what was happening, because it's important to note that Marie Curie discovered these things and she named them, but she didn't know what these things were. You guys know what they are because we've already discovered them. Other scientists later, like Frank Soddy, went through this stuff and started studying what was going on, and they discovered that it was transmutation. It was one element turning into another one, and that was the big thing, is that they didn't want to say alchemy because then people wouldn't listen to them. So they call it something else. So transmutation. So this is what happens for, say, an alpha particle. And we're going to look at different examples for all of them, but I want you guys to see that when I start doing this stuff, everyone has this feeling like, oh God, it's chemistry, and we're doing all of these balancing chemical equations again. Sort of, but it's nothing like that. It is super easy, and if you're overwhelmed, it's just because you really didn't like chemistry, and I get that. I didn't like it either. But this is actually super, super easy. So in the reaction of an alpha decay, what's happening here is you have a very large element to start with that splits apart into an alpha particle and something else. So in this example, it gives us all of the information, but let's pretend like we don't know that thorium, this thing here in the middle, let's pretend like we don't know that that's there. Let's say I gave you a question and I said, hey, you start with uranium-238, and it decays into something and an alpha particle. How can we figure out what this something is? It's actually very easy. Because uranium-238, as indicated by the name, has 238 things in the nucleus, right? And uranium, because it's uranium, has 92 protons. And so that's what it says here. Okay. Has 92 protons. Okay, you're going to be like that. Okay. So it has 92 protons, and so 92 protons plus 146 neutrons gives us 238 things in the nucleus. Everybody with me? So if we say that it decays, this is the reaction, the arrow here, it decays into something and an alpha particle. Alpha particle is a helium nucleus. That is the definition of an alpha particle. That means it has 2 protons and 2 neutrons, or 2 protons and 4 things in the nucleus. Everybody okay with that? So let's start with the top number, 238. So there's 238 things in the uranium nucleus. This thing has 4 of them now. So what's 238 minus 4? 234. Boom. Now that by itself is not going to give you the element, but it will tell you how many things are in the nucleus. So then you go, okay, this thing has 92 protons, and the alpha particle has 2 of them, so it's 92 minus 2. It's 90. And if you didn't know what it was, you could look at a periodic table and go, what's 90 on a periodic table? Well, let's store it. Does that make sense? And that would be the entire problem. And I hope you guys realize that this is not like balancing chemical equations. You're not saying like, oh, what's the coefficient in front of these things or to include X-rays and neutrons, because they can do a lot of damage. So alpha particles are very large. They're, again, helium nuclei. They can do the most damage because they are the largest. They have the most momentum. But because they are the largest, they're the easiest to block. That essentially, literally a piece of paper can stop alpha particles. You just put a piece of paper up. Matter of fact, if you see somebody in like a radioactive hazmat suit, those things are basically just made out of paper, because that's all you need to block them. Now the problem is that you can get other things stuck to it, which is why we want to throw them out. But it doesn't take much to stop an alpha particle. But when I say alpha particles are the most dangerous, it's because whenever they hit something, they will destroy it. They will destroy your cell, they will destroy your DNA, because they are so large. Does that make sense? Like, they will hit it and they will essentially burn it, because of the kinetic energy involved in the impact. But they're very easy to block, right? Because essentially a piece of paper has enough atoms in the way that it'll just run into one of those. A beta particle, which again is an electron, it's a little bit harder to stop, but it's not nearly as bad for you because, well, it's just not as big. It's still going to travel with a pretty good speed, but it could do some damage, but again, it's smaller, so it has less interaction. And that's kind of true for these things as we go down, that they're smaller, they have less interaction, they tend to do less damage, but the problem is as they get smaller, go from beta to X-ray, gamma ray, and then even just a neutron. Technically, gamma and X-ray are smaller than neutrons, but neutrons are harder to stop because they interact with even less. Because at least electrons are negatively charged, and they'll be like steered towards or away from atoms because of other electrons. X-rays and gamma rays are created by accelerating charges, so they can get absorbed pretty easily by electrons or even protons and neutrons. But neutrons just don't really interact with much, and so they can penetrate pretty far. So as you go down here, technically the damage from these things gets less and less, but because they can penetrate so far, it's really difficult to block them. And so as a result, if you have something that's super radioactive and you put something around it, the radiation can still come out through that, especially if it's a gamma ray or a neutron. And so you have to put layers upon layers of things to block this radiation. And so gamma rays themselves aren't terribly bad for you, but the fact is that if we can't block it, if this gamma ray passes through 140 people, it's going to do damage in at least one of those. Does that make sense? And so that's what makes radioactivity a very interesting subject, because how much or how many gamma rays does it take to hurt you? Technically one, but that one has to do some sort of interaction. And the odds of it doing an interaction are pretty low. But again, as you increase the number of, say, gamma rays or X-rays or whatever, the ability for it to do damage increases because the ability for it to actually run into something increases. And so radioactivity is a very interesting subject. So here, this one I want to spend a second on. So these are more like actual examples of problems that you guys would have. And so here, this first one says this is an alpha decay. We have CM, 96, that decays into a helium, alpha particle, plus something else. So let's figure out what this thing is. Well, this is pretty easy. We just did one like this. So if we do this, let's look at what this is going to be. So CM has 247 things in the nucleus and 96 protons. So when we're looking at, say, this helium nucleus here, so it's 247 minus 4. What was it? 243. So our element, our mystery element here, has 243 things in the nucleus. So now it's 96 minus 2. 94. So our element will have 94 protons. So what element, looking at our periodic table, that has 94 protons? Pu. That would be plutonium. Plutonium 243. So that would be your answer. Does that make sense? So Fm257 has 100 protons in the nucleus. Then it says an electron comes out. But it's all about conservation of charge, conservation of mass. So my first question for you, is an electron a proton? No. Is an electron a neutron? No, it is neither of these things. Now we said that this thing comes from a neutron becoming a proton. We'll get to that in a second. But an electron is coming out of the nucleus. It is not a proton or a neutron. So how many things are left in the nucleus? How many did we start with? 257. And if nothing comes out, what's left? 257. Well, that's pretty easy math now, isn't it? Now here's the tricky part. You have to remember that beta decay is where a neutron becomes a proton. So if I had a total for the number of neutrons, I would subtract 1 from that total, but I don't have to write that down, and I would add 1 to the number of protons. So how many protons do I have? 100. So if I add 1 to it, how many do I have? All right, 1. What element is that? Mendelevium. It's named after Mendeleev, the guy who actually invented the periodic table. Which is funny, because it only took the 101 to name one of them after him. Einstein was number 99. Like, come on, really? What's up? I don't remember. I think 100 is like francinium. Like there's curium, which is 96. Berkelium, which is 97, Californium, which is 98, Einsteinium, which is 99. Like 102 is like Nobelium.
Who comes up with these names?
It says right there, it's the International Union of Pure and Applied Chemistry.
So why are they so bad names?
Well, they're named after people.
And they just put on at the bottom?
Huh?
And they just put
On
on.
it, yeah. Yeah, essentially. So these elements up here that you're seeing on the periodic table probably all have names now. And what's funny is for the longest time I didn't realize this, but like literally like these are unnamed elements, and so this is element 114 or whatever, because it has 114 protons in it. But what's interesting is that this is essentially the phonetic spelling of on 4, like 114, 113, 112, sorry, 111, 110.
So I don't think.
Oh, well, this was printed, we didn't have it. We do now. Because we were making it. Well, it's based on the number of things in it. We couldn't get 113 for a while.
So how come those come in with those then?
They just hadn't been designated when this thing was printed. Probably 2005. But like now, I think we go all the way up to almost like 120 or something. So everything through whatever the heck is under number 86 there has been, I think, named even today. Okay, so that's the periodic table. With that aside, so does this make sense how we arrived at this answer? So whenever you do beta decay, you know that mass number is not going to change. And all you have to do is just add 1 to your atomic number. Easy, right? Now let's do gamma decay. Well, gamma decay should be a photon coming out. So is a photon a proton or a neutron? No. So your atomic mass number stays the same. So in this case, 235 stays 235. But it's not a beta decay, so nothing's, a proton's not becoming a neutron, or a neutron's not becoming a proton. Then it still has 92 things, 92 protons in the nucleus. And that one seems the weirdest. Because you're like, but there's no math to do. So first of all, gamma decay, easiest math ever. You don't do anything. Now to actually explain what's going on here, there are different energy levels, which we're not really getting into. And essentially, in one nucleus, each proton or neutron can only occupy a certain energy level. Once this energy level is full, it's kind of like the electron shells for your electrons. That like once the inside shell, how many electrons go up your inside shell? 2. It's essentially a thing like that for protons and neutrons as well. That the lowest energy state, there's only like 1 or 2 I think 2 for protons, 2 for neutrons, available, and everything else has to be above that. I think that makes sense. But here we just talked about, like, for alpha decay, like an alpha particle comes out. It's literally 2 protons and 2 neutrons. Well, if it just so happens that those 2 protons were the 2 protons from the bottom of your energy level, they came out. Well, guess what's at the bottom of your energy level now? Nothing. And so think about, like, you lost an electron, but instead of losing a valence electron, you lost one of the inside electrons. Well, that's where they want to be, and so what's going to happen is if you lost one of those inside electrons, one of the upper electrons would fall down to that lower energy level, and they would release the energy as a photon of light. The same thing happens here. You know, it falls down into whatever hole was created, because when this thing goes shooting off an alpha particle inside, it has no reason to do a higher one than a lower one. It's just whatever's stuck on the edge. Just that one's gone now. And so when it falls down, it releases a photon of light. But here's the deal. These energy levels are so high for for neutrons and protons, that the lowest energy given off is a gamma ray, which is a huge amount of energy. So it doesn't make any sense because you don't really see anything happening here in terms of the numbers. But if you understand these energy levels, that essentially, like a proton maybe fell down to a lower energy level. Well, when it did that, it had to get rid of its energy, and it gives it off as a gamma ray. And so that's one of the things it said on the previous slide when it said things about them. It said that gamma rays usually occur after, you know, alpha or beta. Does that make sense? But essentially, you have a hole there, and beta and gamma are essentially trying to fill that hole through different processes. Are we okay with that? Okay, because yeah, in terms of the math, that's super easy though. So if you get a problem, you know, on your review or test, it's like, hey, you have, you know, uranium-235 undergoes gamma decay. What comes out? Well, that's a very simple answer. Does that make sense? Okay. So here, this slide talks about half-lives. And so what half-life is it's a very interesting thing, because we can't actually predict when something will decay. We know that if we have enough of it, it has this trend to decay in a certain amount of time. That's what half-life is. Because it's a random thing that happens. It's random when the nucleus decides to throw out an alpha particle. But the thing is if we have one of them, I can't tell you when that one particular one would decay. It could decay now, it could decay in 30 years. I don't know. But if you have, you know, several trillion of this particular atom, you can watch them decay over time, and you can determine a rate, and you can make a little graph. And it will have a curve, and we call that the half-life curve, because the curve, as they say mathematically, will asymptotically approach 0. Well, what do I mean by that? You guys should know. So if you imagine a graph of like the number of atoms versus time, all half-life curves look like this. They go. So they asymptotically approach 0, which means that technically, mathematically, they never reach 0. Okay? So that's ideally what you would want. It's okay, how long does it take for all of them to decay? Well, we can never predict that. We can never predict all of them any more than one. But what's interesting about this curve is that if I started with, say, 100 atoms here, that at some point, I will have 50. Like 0, we never technically reach, but do y'all see that 50 is definitely a point on that graph? That this time, right here, is called half-life. That is the time it takes for half of your elements to decay. That's all half-life is. We're not going to get into this whole asymptotic curve and predicting all that. But simply half-life is, okay, if you have a trillion atoms, how long will it take for half of those to decay? Random. And that is half-life. And so here, this table lists several different elements and their half-lives. You'll notice that hydrogen, the isotope H31, which means it has 1 proton but 2 neutrons, that is known as deuterium, I think. Is it tritium? Something. That's all right. has a half-life of 12.3 years. That means it will radioactively decay. That carbon-14 we talked about earlier takes about 6,000 years to radioactively decay. Cobalt is about 30, so on and so forth. What's interesting here is that some of these are very short. Like, look at polonium. Polonium, 0.7 seconds. What's interesting is if you give something essentially 10 half-lives, we consider it not to be radioactive anymore. So essentially after 10 seconds, we don't have to worry about this polonium anymore, do we? But look at something like, say, uranium. Uranium-238, the most common form of uranium, has a half-life of 4.5 times 10 to the 9th years. 10 to the 9th is how much? Billion. Which means, for an average atom of uranium, it will take 4.5 billion years for it to decay. To put that in perspective, we think the Earth is 5 billion years old. So that's a long time for that stuff to decay. And so here, this chart right here, kind of shows you the half-life of uranium. And so uranium, when it decays, it becomes thorium, then it becomes protactinium, then uranium again, then thorium, then radium, then radon, then polonium, then radon is a radioactive gas. So what's interesting about these things is that that rock I told you about Marie Curie studying earlier would have had all of these things in it. Because uranium decays into that. So even if it's pure uranium to begin with, and you wait, say, 4.5 billion years, half of that uranium will have decayed into all of these other things here. And so here it says, okay, like uranium becomes thorium when it gives off an alpha particle. Well, thorium becomes protactinium when it gives off a beta particle, and so on. You guys don't have to like memorize this or any of that. I just want you guys to see that eventually, what we call these things, like this is the nucleus we start with, is uranium-238. All of these things we call, the technical terms, we call them daughters. So these are all considered to be daughters of uranium, all the way down until you get to lead-206, because lead-206 is stable. Okay? That is the common form of lead. And you'll notice that there's a lot of transitions here. Now, some of them take some time. Some of them take 4.5 billion years. Some of them only take 26.8 minutes. That one takes incredibly short amount of time in terms of seconds. So it's interesting when you're looking at that. Wait, yeah, there's stuff on this table there. So right next to the pot chamber, but the radioactive material. Okay, so does that make sense for half-life? Okay. Change this. Okay. So then we come to a thing called carbon dating. This is not where you take carbon out for dinner. What is happening here is we talked about carbon-14. Your bodies are made out of carbon. Most life forms on this earth we consider to be carbon-based life forms, which means we need carbon to arrange all of our structures around. As a result, you tend to have this high amount of carbon in your body. But your body doesn't care if that's carbon-12, carbon-13, or carbon-14. But carbon-14 is radioactive, which means after about 6,000 years, the carbon-14 will decay. Well, it tends to decay into nitrogen. And so what's interesting is that we can do carbon dating because we can look at something, say like this stick here, this piece of wood. It should have carbon in it, but we can look and we can see where it has neutron where carbon should be, because that was radioactive carbon. And we can use that to figure out just how old this thing is, or approximately. And so here, if you have essentially 50% of the radiation coming off of it that we would have expected, it's one half-life. It has a quarter of that. It's got 2 half-lives, and so on and so forth. And so we can predict, for several thousand years, just how old some of these things are. So when somebody says, oh, we found this bone and it's approximately this old, well, first of all, it's a range. It's never exact. But second of all, it's usually based on carbon-14, which is pretty good for organic life, at least on this point. Does that make sense? But carbon dating only works for about 60,000 years. Anything that's older than that, we have to use some other form of radioactive dating. Nuclear medicine. Okay. So all of these things that we are talking about, we say they started kind of with this Manhattan Project that you guys know of. And everybody wants to focus on everything like, you know, atomic bombs and the Chernobyl nuclear disaster, which absolutely need attention. What's interesting here is that there are other things that we use radioactivity for. So what's interesting here, what do you think this image is? Someone swallowing something. Which is interesting because this is actually not an X-ray picture, this is an X-ray video. Okay? So most of you have probably had an X-ray, but most of you have not probably taken an X-ray video. Because they want to observe somebody swallowing, which is the whole point here. But what's interesting is that, can you see things outside of bones and X-rays? Not really. So the stuff that they would have them swallow in this is typically what we call barium. It's radioactive barium that they're swallowing. It tastes kind of like a chocolate. And so when this person is swallowing it, it shows up on the X-rays because it's radioactive. Like it is giving off X-rays and gamma rays when you swallow it. And so what's interesting here is that yes, the X-rays have a chance of giving you cancer, but literally they're having them eat something that is radioactive. Which, yes, could give you cancer. So you might ask, well, why would you do this? Well, there's different reasons. And it lists right here, they get cancer, brain tumors, organ damage, and brain activity by analyzing these things. Because the thing is really only bones show up in X-rays. So if you want something else to show up, well, you need a way for it to give off X-rays. And so there's different things, there's different pills, there's different materials that we can have people swallow, or we can inject them. And there's different things, different parts of your bodies that will take up things. Now, if it's something that you know, in this case, if we're studying the throat, well, really, any liquid going down your throat could give us a study of that. I actually have some personal experience with the swallow study, because not one, but actually two of my daughters have had to undergo swallow studies. Now, one of them in particular, my middle daughter, has to do a swallow study. Now she only has to do it about once a year. And so what's interesting is I take her to the doctor, and they put her in the X-ray room, and they sit the X-ray table up on its side, and they put the X-ray machine next to her, and they blast her with X-rays so they can take a video. And I've attended this a few times. Usually my ex-wife takes her, but when I go, what I think is amazing is I can sit here, I can watch this video, the nurses will help her drink it, and the doctor is just watching the footage come into the video. And what they're looking for is they're looking for what are called aspirations. So aspirations are when you swallow, say, liquid, and instead of it going down your esophagus into your stomach, some of the liquid goes into your lungs. Should liquid go into your lungs? No. And so that's what he's looking for, is an aspiration. And so what amazed me is watching this in real time, there was another nurse standing behind him, and he would just watch her swallow it, and they would jot down, he'd be like, aspiration, aspiration, penetration. Penetration is where it goes in, but it comes back out. And so she would swallow it, and he'd be like, okay, now try this, and then they would just write down as it was happening in real time. I could see nothing. This is really slowed down. And so that's what he did for us, is that after, the experiment was done, he would play back the video. He'd be like, okay, you can see right here, this is what I was talking about. She aspirated a little bit of this. Now, you might ask yourself, why would I do this? Why would I suggest? When we started doing this, my daughter was only 6 months old. So why would we subject such a young child to all of this radioactive material? Well, it turns out that my extremely young daughter has a problem when she swallows. Most of the time when you swallow, your esophagus squeezes the food and it goes down, and squeezes it and goes down. That's how you swallow. esophagus doesn't work like that. Her esophagus just kind of just squeezes everywhere all of the time. And when she gets food or liquid, eventually gravity pretty much wins and overcomes it. But the problem is that as it goes down, her esophagus can squeeze it back up, and that's where it ends up going into her lungs. And so before we knew what was going on, she was getting deathly ill because she had a ton of liquid in her lungs. And she wasn't able to breathe. And we thought it was a problem like she had asthma or something. No, the problem is she has liquids like water, orange juice, milk, whatever she drank, in her lungs. Without this study here, we would have no way of knowing that, except unless they decided to do surgery. So one of the things I can really emphasize with nuclear medicine is I want you guys to understand that sometimes people voluntarily will get blasted with x-rays or literally eat radioactive material to see what's going on inside, because sometimes we just have no other way. Because before this, our only solution was basically every year. You know, in the fall, she would get sick, and usually right around December, we'd go to the hospital for 2-3 weeks because she could not breathe. And it was really strange growing up because literally with my daughter, she was the only one that had this issue, so my other daughters didn't have it. But what was really strange is she would try to drink water that one of her sisters had left, just a cup of water sitting there on the table. I would have to run across the room and like slap the water out of her hand and yell at her like, "Don't drink water, that'll kill you." Which I admit is a pretty strange thing to see. But you know, her being only 2, 3, 4 years old, she couldn't really understand it. So our solution for this is we had to do what is called thickening her liquids. Yes, we had to put things into her liquids to make them thick enough so she wouldn't swallow them into her lungs. Now she's old enough now that she doesn't really have much of an issue with it, like essentially her esophagus is big enough that it's not that big a deal, but she still does aspirate from time to time, which can be a little problematic. And the thing is once we learned this, even if she drank water, just regular water, if she drank too much of it, well, we have one or two options. One, take her to the hospital and have the hospital do this, or two, I could do it. They gave us a little machine that I can jab down her throat into her lungs and suck the liquid out. None of this is fun. Nobody asked for this. Do you think my daughter asked for this? Like, this is probably a genetic disorder that she has. She doesn't want this. But I try to emphasize this, that like without nuclear medicine, we would literally have no idea what was going on. Because even if you cut her open, she's not going to be drinking while you have her cut open. So how else are we going to acquire this information? And so yes, could this stuff give her cancer? Absolutely. Does it increase her risk of cancer? Yes, literally every time she does this, every year. And she's going to have another one this summer. But when you compare that risk to, say, dying because you can't breathe, well, the risk of dying because you can't breathe is way bigger than the risk of getting cancer or something like this. So I like to emphasize this because a lot of people don't quite understand why people would voluntarily do this. And obviously my child was not old enough to give consent, so me and her mother had to do that. But even when you are older and a doctor starts talking to you about like chemotherapy or something, that's what chemotherapy is. It's taking in radioactive material into your body to help kill the cancer. They will explain the risks to you. Like, there is no illusion about the risks. Like, the doctors didn't lie to me about what was going on. This is not a picture of my daughter for you. Her pictures are smaller. Can't really see them. Okay. So here, this kind of talks about some different types of nuclear medicine, like the iodine, radioimmunotherapy. I'm not going to get into that. If you're interested, it's listed here, plus that slide that was linked on the last one. You can look up some more information about that, but I've already spent enough time talking about nuclear medicine. And this is essentially where we're going to stop. Well, no, let's go ahead and do this slides here, atomic spectra and the photoelectric effect, we've already covered. And we're covering them again because this is the connection here. We've already talked about light, and so we talked about how light is caused by photons, and so they have energy levels. So literally here, if you think about,
Hey, once you do the isotope, are you doing anything with the fire extinguisher, the fire, the Millennium and the fire detector?
no, I'm just saying what it
You
is.
just let it sit right there?
Yeah.
You're not doing any more demo wise?
No.
Okay, cool, thank you.
Okay, so here we're talking about, like, if you assume that this is a proton emitter, just hydrogen. Hydrogen will have one proton and one electron. And so the electron wants to sit in its lowest orbital level, that first shell. But if a photon of a particular frequency comes in, it will jump up to a higher energy level. It will absorb that photon of light, the frequency. And then when it falls down, it will give off that same photon of light. And so here we talked about this in the last unit, that each element has its own atomic spectrum. So hydrogen has particular spectral lines, helium has lines, carbon has spectral lines. This is because of the electrons jumping up and down in your energy levels. Does that make sense? So here, this is the photoelectric effect again, which we've already talked about. But that's how important the photoelectric effect is. Like, it's in 2 units now. The photoelectric effect is where electrons are emitted from an object when the frequency is of the electromagnetic radiation is correct. All right. So we're going to go ahead and stop here for today. We're going to finish these